On the weekend before the ice storm, our last geometry class, we began with some board work to review some concepts. Then we got our quizzes back from sections 1, 2, and 3 of chapter 4. Then we had a short lesson on the short section 4.6, similarity transformations. If you were absent, then continue watching this video, but you should also read section 4.6 in the textbook. In groups, we asked, if a figure undergoes translations, reflections, and rotations, will the image be congruent to the pre-image? And the answer was yes. When we asked why, groups discussed, these are rigid transformations. When you reflect, rotate, and translate, the shape doesn't grow or shrink, doesn't change shapes. It stays exactly the same. It's rigid. So, yes. Then we changed the question and said, what if the figure undergoes translations, reflections, rotations, and dilations? Now is the image congruent to the pre-image? And the answer to that was a resounding no. But they will be the same shape. So they'll be bigger or smaller, but they will still be the same shape. And that word was similar. For example, these two triangles may be similar if they're the exact same shape, but different size. So this idea of similarity, how do we know if they're the exact same shape? And how are they related to transformations? Well, the second question is easy. If you have a dilation where the shape gets bigger or smaller, then you'll have similar objects. Similarity will always require dilations. The next thing that groups did at the board was dilate the orange triangle tray with center C and a scale factor of 3. So students reviewed doing that in groups, and in a nutshell, it looked like this. For every one of the 3 vertices, we draw a line from the center through that vertex. Keep going. From the center through that vertex right there. Keep going. From the center through that vertex. Keep going. Then we consider that distance from the center to this point T, and we do that distance once, twice, 3 times. And that's where we put T prime. And why 3 times? Because the scale factor is 3. Now let's do it for the green line. So from the center to point R. One of those distances, 2 of those distances, 3 of those distances. And that's where R's image, R prime, goes. 3 times further away from the center than R is. 1 time, 2 times, 3 times. And then finally for point E and its image, E prime, we take this blue distance and we move that distance 3 times. 1, 2, 3. And there's our E prime. Now we will erase all these markings we had, and then connect our image points to get our new image triangle, which is the result of a dilation scale factor 3. Okay, and then the last board work we did was a dilation when you're given coordinates. We learned last class, when you do a dilation with coordinates, we will always assume the center of the dilation is 0, 0. And all you have to do is multiply the scale factor times all of the coordinates. So 1/2 of 12, 1/2 of -8, 1/2 of -8, 1/2 of -6, 1/2 of 0, and 1/2 of 10. So half of these coordinates gives us E prime, 6, -4. And Z prime will be a half of these coordinates, so -4, -3. And P prime will be a half of these coordinates, which is 0, 5. That's it for dilations when we have coordinates in which we always assume the center is the origin. And it certainly looks like the green triangle has been dilated to a triangle that's the exact same shape. It's similar. And the scale factor was 1/2, which means this length is 1/2 of the corresponding this length. The length of P prime E prime is exactly half as long as the length of segment PE. And the length of image Z prime E prime is exactly half the length of the pre-image segment ZE. So that completed the board work we did in class. Then we got our quizzes back. People got to ask a lot of questions. And then we talked about section 4.6. Section 4.6 is about similarity transformations. If two shapes are similar, then they are the exact same shape, although they may be different size. And in terms of transformations, if two shapes are similar, then they required a dilation. Then we got right into examples. So our first example, example 1, will be number 3 from the textbook. You can see that this composition of two transformations, a dilation followed by reflection, is definitely going to be a similarity transformation because it includes a dilation. All right, let's find the coordinates of the image after this similarity transformation. So our first transformation will be a dilation where all the coordinates get smaller by a factor of 3/4. So let's multiply all of the coordinates by 3/4. When we multiply all these by 3/4, we get these image points. Practice your fraction mental arithmetic when you multiply these by 3/4. Get your answers in fractions. But that's just the dilation. Now we need to do the reflection. And what happens to an x and y coordinate when we do a reflection in the x-axis? That's a question we may have memorized, or we can just think to a really quick thumbnail sketch. And we're going to flip over the x-axis. So we're going to take this point and flip it over the x-axis. What will its coordinates be? The exact same distance to the right as before, but instead of going up y, we'll go down y. So any point after reflection in the x-axis will go from xy to x, the opposite of y. And that's how we'll complete this. We'll take these images and reflect them in the x-axis, which follow this rule. So the only thing that changes are the y coordinates. The x coordinates all stay exactly the same, and the y coordinates change signs, -1.5, +3, and +3. All right, now we can graph our original triangle and the image after this similarity transformation, which is a series of two, or a composition of two transformations, one of which had to be a dilation in order to be a transformation that resulted in a similar image, that is, a similarity transformation. So the graphs look like this. And our pre-image is in yellow, and after the dilation and reflection, we're in purple. So this yellow thing will map onto the pink thing with a dilation and a reflection. Therefore, these two shapes are similar. And I'd like to point something out. When shapes are similar, the ratios of corresponding sides will be the exact same thing. So, for example, the yellow triangle's shortest side, GH, corresponds to G double prime, H double prime. What is the ratio of GH divided by G double prime, H double prime? 2 units long, 1.5. 2 divided by 1.5 is 4/3. Similarly, this long vertical side, GF, is 6 units long, and it corresponds to G double prime, F double prime, which is 4.5 units long. Well, the black side divided by the corresponding orange pink side is again 4/3, or 1.3 p. Same thing for the hypotenuse. If you use the distance formula, the black hypotenuse divided by the pink one is root 40 over root 94, which is 4/3, or 1.3 repeating. So that wasn't something this problem asked you to do, but remember, if you do a similarity transformation, which involves a dilation, then your shapes will be similar. And if they're similar, then when you divide a side by the corresponding side, the answer is always the same. So the shortest black side divided by the shortest pink side, 4/3. The medium black side divided by the medium pink side, 4/3. The longest black side divided by the longest pink side, 4/3. All right, let's look at example 2. So we're mapping the blue to the green. So we must have a dilation that's getting bigger. So what will the scale factor be? Well, let's look at these corresponding sides here. For example, the ones on the right. This segment length is 2, and this segment length is 4. We're going from the blue to the green, and those are corresponding sides. So what are we multiplying this side by to get the bigger side? 2 times 2. Therefore, the scale factor will be 2. So next, let's consider what happens after a scale factor of 2 by actually looking at what the coordinates are for our blue preimage and what happens to them after a dilation scale factor of 2. So points D, E, and F have these coordinates, and if we do a dilation scale factor 2, we just multiply 2 times all these coordinates. So let's go ahead and plot these and see what it looks like in relation to our final resting place, which is we're trying to land on the green one, this big one on the outside. So where are we right now after this dilation? Well, you can see where we are, and this should be the exact right size, but we just need to do a little translation next. And you can see that to get to the green image, our red shape just needs to slide up 1 unit. And that's how we complete this problem. And we can describe that translation either by using a vector. Remember, this vector tells us we will not move left or right at all, but we will move 1 unit up. Or we can use the rule notation where every value changes horizontally, not at all, but vertically by moving up 1 unit. All right, we described the transformation that maps the blue shape to the green shape, and the process was to do the dilation first and to find 2 corresponding sides, find out how long they were, 4 and 2. So what do we have to multiply by the preimage by? Times 2. Looking at what that does to every preimage point, everybody gets multiplied by 2. Considering what next needs to happen, slide up. So the second transformation was a slide using this vector or this rule. All right, the third and final example. Determine whether the polygons with the given vertices are similar. And if they are, we'll use transformations to explain the reasoning. And if they're not, we'll explain why not. So, first of all, we might graph these to get a picture to see whether it's obvious or not. So let's do that. Well, it looks like these shapes might be similar. We're going to use transformations to explain our reasoning. All right, so if they were similar, one of the key ideas is that there will definitely have to be a dilation. So if these shapes are similar, there would be a dilation. And what would the scale factor be? Well, let's focus on these corresponding sides. EF looks like it corresponds to BC. How long are they? From E to F is 1 unit, and from B to C is 1, 2, 3 units. So if these guys are similar, then the dilation will have a scale factor of 1 times 3. There'll be a scale factor of 3. So if we go from the small one to the big one, we have to multiply all the coordinates by 3. So we're going from green to blue. So let's take the green coordinates and multiply them all by 3 and see what we get. Well, everybody times 3 gives us 0, 9, 3, 15, and 6, 15. Where would that be? That would make this little green guy dilate up to the red guy. And now notice they're the exact same size. So our second transformation, which will complete our similarity transformation, will be a slide, sliding the red one onto the blue one. I'm going to use a vector because it's the least amount of work. So let's start with this point right here, this red point, 0, 9. That needs to slide to point A. So we're going to have to move to the right. 1, 2, 3, 4, 5. We're going to have to go down 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, we needed to go to the right 6. So 6 to the right and 9 down. Again, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we translate by this vector, that point will land on A, this point will land on B, and this point will land on C. And we're done. And if you prefer, you can describe that translation this way using a rule. Every point will be mapped onto a point that's 6 to the right of itself and 9 below itself. So there you have it, dilation and a translation. Dilation is a scale factor of 3. All right, that concludes a description of what we did in class that last day before the big ice storm. Moving forward and looking ahead, our next time together will be a review day, and the second next class will be our test on chapter 4, where we are skipping section 4.